All right, so we'll go through some of these questions from this week's module topics. And we're covering in lecture this week a couple different topics. We're looking at chemical quantities, chemical equations, chemical reactions, and then the calculations involved in those. In addition to that, we're also looking at gases. So we'll first of all take a look at some of the gases problems. And just as a quick reminder, as you're going through some of the videos, you'll see that most of the calculations here really boil down to a little bit of algebra and manipulating equations. We're just now applying it to the different gas laws. Okay, so for most of these, we're going to use our gas laws in our calculations. And probably the most challenging thing here is to decide, once you have a question, is which relationship or which gas law you're going to have to use. And all of that, you can decide that by looking at the information that's given in the question. So as a general strategy, what you may want to do is to write down the information that you're given, what you need to find, and that will usually help you figure out what relationship or what law is going to be most useful. So in this first question, it says the cylinder is filled with 10 liters of a gas. So that's a volume. And the piston is put into it, and you have a little diagram here. And it says that the initial pressure, so the pressure P, is 103 kilopascals, and kilopascals and pascals just one of the many units of pressure that we'll see. Most commonly, we see atmospheres and we see millimeters of mercury, but there are other units of pressure. All right, so this is what we're starting with. And it says the piston is now pulled up, expanding the gas until the gas has a final volume. So final meaning we're going to end. So starting is initial, and ending would be final. And the final volume now, we're told, is 23.0 liters. And we need to calculate the final pressure, right? So in this case, we're told explicitly, we don't know what this is, we need to calculate it. So we're looking at volume and pressure relationship. We are given the initial volume, which we express as V1, the initial pressure is P1, the final volume V2, and then the final pressure is P2, and this is going to be our unknown. So in this case, we're looking at the PV relationship, and that is Boyle's law. And it's all well and good to know the name of the law, but what's more important is that you know the actual relationship between pressure and volume. And that relationship is P1 times V1 is equal to P2 times V2, right? That's the most important thing from the relationship. So in this case, P2 is our unknown. That's what we need to find. So we need to rearrange this equation. We need to solve it for V2. I'm sorry, for P2. All that means is to isolate P2 on one side and move everything else to the other side of the equation. So in order to get rid of the other thing that we have on the right side, which is V2, we can divide the right side by V2 so that they cancel. And whatever you do to one side of the equation, you need to do to the other side. So we divided the right side by V2, we need to divide the left side by V2 as well. So now we have our P2 isolated. Everything else is on the other side. We can then substitute the values into our rearranged equation. And we know what the P1, V1, and V2 are. So P1 is 103 kilopascals. I'm sorry, 103. V1 is 10.0 liters, and V2 is 23.0 0 liters. So you'll notice that when I set this up, I'm not just putting the numbers in, I'm also putting the units, because when I look at the units, I can see that liters cancel. I end up with kilopascal as my unit. That makes sense because I'm trying to find a pressure. All right, then you'll go ahead and evaluate this. Use your calculator, and you want to round it. In this case, we have 3 sig figs, 3 sig figs here, another 3 sig figs. All we're doing is multiplying, dividing. So our final answer should have 3 significant figures. You want to round it to 3 sig figs. All right. We have here another question that looks at maybe a slightly different relationship. We're told that a weather balloon now is filled with 10.3 liters of helium, and the temperature, so this is a volume, V, right? Liters is a unit of volume, and the temperature inside the shed is 11 degrees C, so that's T, obviously, and that's what we're starting with again. So this is our initial conditions. So we can say V1 and T1. And then the balloon is taken outside where the temperature now is negative 22 degrees C. And we need to calculate the new volume, which would be V2 of the balloon. So this is our final, these are our final conditions. And then we're also told here that we can assume the pressure is staying constant. So P doesn't change. And then because the gas is in the balloon, the amount of the gas doesn't change as well. So we're looking here at just the VT relationship. And that's Charles' law. And that relationship is V1 over T1 is equal to V2 over T2. One thing to keep in mind as you're going through the gases chapter, and it's very easy to lose track of this as you're going through calculations, when you're giving temperature, you want to make sure that you convert that to Kelvin. Okay, don't wait to do it because you'll probably forget most likely. So we're just going to add 273 to our Celsius temperature, and that gives, this is 284 Kelvin here. For my T1 and my T2, we're going to add 273 to that as well. So that gives 295 Kelvin as my T2. So that's probably the most common mistake with laws or gas laws involving temperature. So make sure that you don't forget to do that. And then we're going to do the same thing to this equation that we did to the previous one. Our unknown here is V2. Okay, so we need to solve this equation for V2. Okay, and I'm going through it and I'm not putting the numbers in right now. I'm putting the numbers in at the end. You can by all means put the numbers in right now if you want to. There are multiple ways to solve this. I just like dealing with the symbols and stuff first, and that way I can plug in the numbers at the very end. All right, so a couple of ways you can solve this also. You can, again, here we want to isolate V2 on one side. So in order to get rid of the T2 on the bottom, what we can do is to multiply this right side by T2, so it cancels. And if you multiply the right side by T2, you need to multiply the left side by T2 as well. So we end up with T2 times V1 over T1 is equal to V2. And then we can substitute our values into that rearranged equation. Our T2, we converted it to Kelvin. It was 295 Kelvin. Our initial volume was, let's see here, 10.3 liters. And then our T1 initial temperature was 284. Okay, so again, your units, Kelvin cancels, and then you end up with liters as the final unit, which makes sense because I'm trying to find volume. The other thing that you can use here to confirm that you've set up and you've done the math and the algebra correctly is you can check and see, well, what's the relationship between V and T? Well, this mathematical relationship is one that is a direct relationship, which means if we increase the temperature, the volume should increase as well, okay? So when you get your final answer, guess what? We already know generally what that final volume should be. If my temperature went from 284 to 295, so that's an increase in temperature, then my volume should go up as well. So my final volume should be more than 10.3 liters. And if it's not, that means you probably did the algebra incorrectly. All right, and you can go ahead and evaluate this and round it to the correct number of sig figs. All right, and then, like I mentioned at the beginning, there are several different units that we'll see that are being used for pressure. And this question just asks you to convert between those different units. So if you're given, for example, 0.000314 atmospheres, if you want to convert this into millimeters of mercury, then you need a relationship between these two. Okay, and you can look that up in your textbook. Okay, you'll see all of those relationships are given, and then you're going to set that up the same way like you've set up any other conversion. This is nothing more than unit conversions that we're doing. So for every 1 atmosphere, you have whatever you're going to find for millimeters of mercury, right? Whatever that number is, atmospheres cancel, and you end up with mmHg as your unit. Do the same thing for the torr. All right, then the next one. Let's see here. So it's giving you a sketch or a diagram of a mixture of gases. So you have nitrogen and you have oxygen in the gas, and it represents, well, the sketch represents a sample of that mixture. So, and it tells you that in this mixture, the pressure, the total pressure is 600 torr. Okay, so when you add up all of the oxygen and the nitrogen, their individual partial pressures, you end up with 600 torr as the total pressure. So remember now the way that Dalton's law of partial pressure works is that the gases that we have oxygen and we have nitrogen. If I add together the pressure, the partial pressure of the O2 together with the partial pressure of the N2, I get the total pressure, all of those gases. So how do we know what those are? Well, this question is asking us to figure out something known as the mole fraction of the gases. So you have to go in now and take a close look at our sketch and identify which or how many of these different gases you have. So the oxygen is red. So the 2 red spheres, that represents O2. So if we count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We have 15 O2 molecules. And how many N2s do we have? We have 1, 2, 3, 4, 5 N2 molecules. So we have a total number of molecules of 20. Okay, and so these are individual molecules. We can also use moles as well interchangeably because the ratio is going to be the same. So we can say we have 15 moles of O2 and 5 moles of N2, or 15 molecules of O2, 5 molecules of N2. So the fraction now, specifically the mole fraction of O2 is simply the number of O2 that we have, 15, divided by the total, which is 20. So that fraction, and it ends up being, turn it into a decimal. So we end up with, what is that, 3/4, which is the same as 0.75 as the mole fraction of O2. And we don't need to do the other conversion because, or the other calculation, because there are only 2 types of gases in here, and you add them up, they should equal to the whole thing, which is 1. So the fraction then of N2 is simply 1 minus 0.75, which would be 0.25, and we can confirm that if I take the 5 molecules of N2 divided by the total number of molecules that we have, which is 20, that's 1/4, which is 1/4, So we've confirmed that. Okay, so we have the fraction of N2, we have the fraction of O2, the mole fraction. We can then take those and multiply it by the total pressure to figure out the partial pressure. So for example, for N2, I can take the fraction, the mole fraction of it, 0.25, and I multiply now by the total pressure. So this is saying a quarter of the pressure is due to the nitrogen, and that is total pressure there was 600 torr. A quarter of that will give you whatever calculated to be, and then the same thing for the oxygen, for the O2, mole fraction is 0.75, so 3/4 of the entire sample is O2, so we multiply 0.75 times 600, and we get the partial pressure of the oxygen in that sample.